Welcome to the exercise 1 of our hydraulics calculations and hydraulic schematics course. This exercise is going to be simple. It's going to be an intro hydraulic problem. You'll see we don't even have efficiency factors yet. The system is assumed to be ideal with no losses. So take your pen, take your paper and calculator, get ready, and I strongly suggest you follow my calculations. Now, let's read the problem together. It says here, in the adjacent system, the lift cylinder hoisting the load M is operated by utilizing another cylinder, the actuating cylinder. This is the actuating cylinder. Calculate the piston velocities for both cylinders. What would be required for the velocities to be equal? What is the maximum lifting height? What would the maximum lift height be if the stroke length LS1 of the actuating cylinder would be doubled? And E, calculate the pressure PS11 required for lifting the load. Now, let's start with A, okay? So we're going to calculate the piston velocities. Let me just choose my pen. So right here we have some parameters. We have the flow coming in our actuating cylinder. We have the diameter of the front of the piston. We have the diameter of the piston rod. You'll see why we need that. We have the diameter of piston number 2, also the diameter of piston rod number 2, and we have the stroke length of hydraulic cylinder number 1. We have the stroke length of hydraulic cylinder number 2, and we have the weight of this object that we have to lift. Now, first of all, we have to convert our flow to meters cubed per second. Okay, so we need meters cubed per second, and currently we have liters per minute. How are we going to do that? Now, we have 10 liters per minute. Liters are actually decimeters cubed, okay? And there is 1,000 decimeters cubed in 1 meter cubed, in 1 cube meter. So, and we know that there's 60 seconds in a minute. So we're going to divide 10 by 60 because of the 60 seconds times 1,000 because 1,000 decimeters cubed in a meter cubed. And this is going to be meters cubed per second. Take out your calculator and calculate this for me. So the flow in meters cubed per second is going to be 1.67 times 10 on the minus 4 meters cubed per second. Okay. Now we have the flow in meters cubed per second. The second thing we have to do is we have to calculate this area. We don't have the area of the front of the piston. So the area of the circle is calculated by pi times the diameter of the circle, which we have squared, divided by 4. We have the diameter in millimeters. Okay, we have the diameter in millimeters, but we need meters, okay? And how many millimeters are in the meter? 1,000, right? So this is going to be 0.063 meters. You can check that on your calculator right now. Okay, so pi times 0.063 meters squared divided by 4. And what we get for area is 3.12 times 10 on the minus 3 meters squared. Okay, so this is the area of the front of the piston of the actuating cylinder. Now we have both the area and the flow. And remember, we said that flow is equal to speed, velocity, times the area of the piston. Okay, so we here have the speed of the cylinder 1. So from that, we can say that the velocity of cylinder 1 is equal to flow coming to the cylinder 1 divided by the area. And we know that the flow is 1.67 times 10 on the minus 4 meters cubed per second, and the area is 3.12 times 10 on the minus 3rd meters squared. So we can basically do this. So up here we're only going to have left meters per second, and the speed of the piston number 1 is going to be 0.0535 meters per second. This is the speed of our first piston, okay, of the actuating piston. Now we know the velocity of the first piston. We have to calculate the exiting flow. The flow is going to exit right here. So first we have to calculate the area, this ring area behind the piston. So that area, AS13, is going to be equal the area of the big piston that we already calculated. So we have pi times ds11 squared divided by 4 minus pi times the diameter of the piston rod. Okay, so ds12 squared divided by 4. And what we get is, take your calculators, what we get is 2.41 times 10 on the minus 3 meters squared. Okay, this is the area of the back of the piston. Now we have the velocity and we have the area of the back of the cylinder of the piston. Now what we can do, we can calculate the exiting flow. So we can calculate the flow that exits our piston, and it's going to be, we said that flow is velocity, so we already have velocity here. So velocity times the area of the back of the piston, and that's gonna be 1.29 times 10 on minus 4 meters cubed per second. And now if we want to change this to liters per minute, we can just multiply it by 60 times 1000, okay? And we're gonna get QVS13, we are going to get 7.73 liters per minute. Okay, great. Now we are going to calculate the piston velocity of hydraulic cylinder number 2. Okay, so now we know that this flow is going to enter here, and we just have to calculate the area of the piston number 2. And the area of the piston number 2, AS21, is equal pi times the diameter, and the diameter is 40 millimeters. Okay, so ds21 divided by 4 squared, and this is going to be 1.26 times 10 on the minus 3 meters squared. Okay, so this is the area of the piston number 2. And now all we gotta do is we have to calculate the velocity. So VS2 is equal to the QV, I don't have V here, QVS13 that we calculated right here, divided by the area of the piston number 2. So that's gonna be equal to 0.1026 meters per second. And this is the velocity of piston number 2. So A is done. Now we're going to talk about B. Okay, now let's do B. B says, what would be required for the velocities to be equal? Now, we know that we are sending QVS13 to the second cylinder. Okay, that's the flow we have. So the flow exiting this cylinder and the flow entering this cylinder is equal. Okay, and we want to know what would be required for the velocities to be equal. So Vs1 to be equal to Vs2. Okay, we know that velocity is equal to flow divided by area. So we're going to write the first velocity. So velocity number 1 is the flow QVS13, the flow exiting the cylinder 1, divided by the ring area, the back of the piston area. Okay, so AS13, we calculated that in A, and this has to be equal to, again, we have QVS13 entering cylinder 2, but now we have the area of the front of the piston, AS21. Now, if we divide this entire equation for the flow, because we have flow on both sides, we can divide it by QVS13. We lose the flow, and what we have left is AS13 is equal to AS21. What does this mean? So this means that we have to have the same area, the same effective surface. So it means that the ring, the back piston side, the ring side area has to be equal to the front of the piston area on cylinder number 2. So that's B. That was quick. Okay, and now let's do C. And C is, what is the maximum lifting height? If you took my Hydraulics 101 course, you know that we used volume to search the stroke of the hydraulic cylinder. Now, let's calculate the total oil volume exiting this cylinder 1. So it's going to be VS13, okay? The volume exiting right here. It's going to be equal to the length of the stroke of cylinder 1 times the surface area of the back of the piston, of the ring side, okay? And that is AS13, okay? Here we have the areas that we calculated before, and I strongly suggest you take out your calculators and calculate this with me. So the stroke of the first cylinder is LS1 is 250 millimeters, which is 0.25 meters. Okay, we're calculating this in meters, times 2.41 times 10 on the minus 3 meters squared. And the exiting oil volume is 6.03 times 10 on the minus 4 meters cubed. Okay, so this is the exiting volume from the piston 1 that exits here. Now, this volume is going to enter piston 2, okay, and we have to find the length of the piston stroke. So let's say that length is x2, because this is piston 2, and that x2 is equal the volume that enters here, so the volume VS13, the volume that we calculated, divided by the surface area of this piston. And the surface area of this piston is right here. We calculated it before. So AS21, and this is going to be equal, so we got 6.03 times 10 to the minus 4 meters cubed, divided by 1.26 times 10 on the minus 3 meters squared. So meters cubed are divided by meters squared. We only have meters left here, okay? And the stroke here is going to be 0.48 meters, which is equal to 480 millimeters. So this is the maximum lifting height for this stroke of the cylinder number 2. Okay, and C is done. So now we have D. Okay, so let's do D. And D says, what would the maximum lift height be if the stroke length LS1 of the actuating cylinder would be doubled? We have to calculate exiting volume flow, but this time we have 2 times the stroke length 1, and we have the back area, the back ring area of the piston 1,3. So it's gonna be VS13 is equal to 2 times 0.25 meters times 2.41 times 10 on the minus third meters squared. And this comes to, the exiting volume flow comes to 121 times 10 on the minus 3 meters cubed. Of course, we could have taken the volume from the C and just multiply it by 2, but I prefer this step-by-step way so you can understand everything. So now we're gonna calculate the stroke length number 2. Let's put max, okay? With this volume, so 121 times 10 on the minus 3 meters cubed divided by the surface area, the surface of piston number 2. So 126 times 10 on the minus 3 meters squared, and that comes to 0.96 meters. But 1 second, it does come to 0.96 meters, and that's 960 millimeters. The problem is the maximum stroke length of this cylinder is 500 millimeters, which means that this hydraulic cylinder, the stroke length, the maximum stroke length, would be 500 millimeters, and when it reaches the top, it will just stop. And the actuating cylinder would stop as well because we don't have any safety valves here. So the maximum stroke length is 500 millimeters. And that's it for D. Now we only have left the E part. Okay, and the last letter we have left is E. And E says, calculate the pressure PS11 required for lifting the load. System assumed to be ideal, no losses. So the pressure right here, this is pressure PS11. Let me take my pen. So first, let's calculate the force that this mass exerts, okay? So let's call that force F2, and of course it's going to be equal to m times g, the gravitational constant, and that's going to be 5,000 kilograms times 9.81 meters per second square. And we are going to get 49,050 newtons. Okay, so that's the force that this mass pushes down on. So the pressure that we're going to need here to counter this force is going to have to be PS21 is equal to this force 2 divided by the area, the front piston area. So AS PS21. And that's going to be equal to 4950 newtons divided by AS21. It's 1.26. So 1.26 times 10 on the minus third meters squared. So we have pressure, so PS21 is equal to, let me just calculate this. So this is 3.8 times 10 on the 7th pascals. Okay, we said that pascals are newtons divided by meters squared, which we have right here. And we have to convert this to bars. And when you're converting pascals to bars, you just divide the pascals with 100,000. Okay, and if we divide this by 100,000, we get the pressure PS21 is equal to 380 bars. Okay, so this is the pressure that's going to be right here. So that pressure is also going to act here, okay, because these two systems are linked together. So now we have to calculate the force that this pressure will exert on this piston. So the force, we're going to call this force F13 because it acts on the back, and it's going to be equal to the pressure we just calculated, PS21, the pressure going in here, times the back area of the piston, the ring area. So AS13, okay? And of course, we have to put the pressure here now in pascals because we are calculating the area by meters squared. So we have 3.8 times 10 on the 7th pascals, or newtons per meter squared, okay, times 2.41 times 10 on the minus third meters squared. And we can do this. Now we only have left newtons, so the force is going to be equal 91,580 newtons, which is 91.58 kilonewtons. Okay, so this is the force that will push this piston rod and this piston to retract, to go left. So our pressure here has to produce a force that is equal or bigger than this. So we can push it, so we can lift this weight up. So we have F12, let's say F12, has to be equal to F13, okay? And now we can say that F13 is equal the pressure PS12 times the piston area AS11. So from this, we can calculate the pressure PS12 is going to be equal force 13 divided by the area 11. And the force we know in newtons is 91,580 newtons divided by the area, which is 3.12 times 10 on the minus third meters squared. So pressure 12 is going to be equal 2.9 times 10 on the 7th pascals, which is 293 bars. So we have to make a pressure that is 293 bars so we can push this piston rod and piston right so it can push this load up. So that's it for E. And that's it for this exercise. Now I would like you to take the same exercise and do it by yourself. Thank you for focusing, and see you in the next lesson.